My name is Chris Down. I work as an engineer on the Linux kernel at Meta. I will work mostly on the kernel's memory management subsystem, especially on resource control, isolation, that kind of stuff. I'm also a maintainer of the systemd project, so already I've given you 2 things you can hate me for. And mostly I work on Cgroups and other resource control management stuff. Most of the time, my job is essentially thinking about how we can make Linux more reliable and scalable. So today I want to talk to you a bit about misconceptions I often see from programmers and system administrators around memory. Memory is a topic which I think many of us believe is table stakes for our job, right? It can be a very emotive conversation to discuss things like, swap, for example, mostly because we already believe that we know the answers. In my 15 years now working with SREs and software engineers, I've seen a lot of misconceptions about how things actually work and also why they work in the way they do. So hopefully you'll come away from this talk with some updated concepts and maybe some new ideas to help your services and systems in production. So let's start off with something basic. Don't worry if I've just given you a shit ton of C to look at. C is not the point. I'm not going to trick you with any compiler or CPU reordering nonsense, but let's just go through this line by line, right? So in this example, we malloc 1 megabyte of memory. We put the string hello there inside it, and then we eventually free the memory after printing it. So now have a little think for yourself. At what point do we actually allocate the megabyte of memory here? What actually happens to the RAM during the life cycle of this application? And what does malloc here actually do? What's the contract it's enforcing? What if I told you, for example, that malloc, despite the name, has absolutely nothing at all to do with memory allocation? So how does this whole sequence of events actually unfold then? First, in order for us to be on the same page, I think it's a good idea to go through like the high-level goals and non-goals we often think of as memory management developers. So if I were to make just a few high-level goals for Linux memory management, it would be something like this. First, we want to make the most possible use out of all available system resources. In our case, that's memory. This is not only a question of making sure the memory is accessible, obviously that's important, but we also need to make sure that applications have the syscalls and operating system support in order to use it effectively. This usually means things like we want all of the system memory to be used all of the time, if possible. Typically, the slack space there is going to be filled with things like disk buffers, file system caches, things like that. We also need to make sure that memory accesses are safe. So for example, if a program should try and intrude on another process's memory and it doesn't have the rights to do so, then we shouldn't allow that. Most of that happens inside the CPU itself. There's kind of a limited amount of kernel interaction, but we do need the operating system support to perform actions based on the complaints that the CPU raises. We also use some of these complaints that the CPU gives in order to improve efficiency, which we'll come back to later. We also need to ourselves use minimal resources while doing this. It's no good having this kind of perfect memory tracking that tracks everything absolutely accurately if it makes the system slow to a crawl, right? That means that if you look at Linux memory management code, you might wonder why something is done in kind of a not correct way. And the answer is almost always that the trade-off is that it has to be done very, very quickly. So we do a lot of approximations and things like that. Performance is pretty critical in this part of the code. We also need to not involve the application's involvement in the vast majority of memory management activities. Realistically, this means that a lot of this efficiency work needs to happen transparently without the application even knowing about it. So especially for our efficiency work, that often requires rethinking how applications even see memory in the first place. And we'll go over some of the concepts which help with this in a couple of slides. So one of the strategies that Linux employs to extract the most out of available memory is something called overcommit. Overcommit is like having a credit card where every time you ask for memory, we're going to give you it. In fact, we'll even happily give you more memory than the entire system has available. So why on earth would some sadist allow such a thing? Well, this kind of ties in with 2 other concepts which Linux has. One is called demand paging and one is called swapping. In demand paging, we don't allocate physical memory up front. We only reserve physical memory for use when the application actually makes use of that memory. And in swap, we permit offloading some already loaded memory to a slower storage, like to the disk or something like that. This is all based on the fact that allocating some memory is a very poor proxy for trying to work out whether it's actually going to be used or not. In fact, a huge amount of memory that programs allocate is either never used or very scarcely used. To keep those pages resident in physical memory then would be pretty wasteful, because then you can't use that memory for anything else on the system. So our goal here is to increase the memory utilization system-wide by decoupling the act of requesting memory from actually physically allocating it. A typical argument you will see on places like Hacker News or other places where people discuss the important matters of the day is that it should be the responsibility of the application developer to do memory management, and the kernel should do nothing about it. I think over the years, with all the security vulnerabilities that we've had, we've proven that humans are pretty crap at managing memory. Not even like doing buffer overs and stuff. We can't even work out what size the buffer should be in the first place. As such, a lot of projects are moving to languages where users tend to have this very abstracted access over memory, like Rust, or even to some extent modern C++. Of course, there are also interpreted languages where you have absolutely no control over memory whatsoever. And even if you do have control over it, it's very hard to say, you know, what size do I need this buffer to be, for example. I think if you see in any sufficiently complex system, it's probably pretty clear why expecting the programmer to do all the memory management and do it correctly is kind of a losing game. It is true that overcommit does have its downsides. For example, if everyone actually does turn up and wants all their memory, then you are shit out of luck. It's not going to end well for you. However, these kind of issues can somewhat be mitigated both in kernel and user space, and we'll come back to some of the approaches for that later. So the way that Linux does this under the hood is by using something called virtual memory. Virtual memory is kind of shared parts from the kernel and from the CPU, where you have this kind of A or multiple levels of abstraction over memory. For example, some memory might have been virtually given to an application, but it's never physically reserved. Each process is given its own virtual address space. On Linux, we call this a VMA. Well, inside a virtual address space, you can have one or more VMAs, which is a virtual memory area. And this virtual address space just looks like normal memory to the program. It doesn't really have any inkling of what that is. But it doesn't actually have any memory contained. It's just a mapping. A virtual memory address doesn't actually even have to be backed by RAM, right? It could equally be backed by something like swap, for example. And then when it's accessed, we have to promote that to main memory to be accessed. It could also not be mapped at all, like in the case of the demand paging case, where you kind of gradually page something in. In that case, we need to, as the kernel, work out, is this not mapped because the access is invalid, or is it not mapped because it's valid, but I have to do something to get the page to be in the state to be readable? This, of course, doesn't prevent you from accessing a valid but wrong part of your program where you have direct memory control. Really, we can only stop you messing with other programs or like things related to, you know, having the wrong permissions for the action you want to do on the memory. But the rest is kind of a little bit up to you. So we kind of mixed two different concepts there, overcommit and demand paging. So demand paging is what we were discussing previously, where you don't actually allocate physical memory until it's demanded. And this demand typically comes in the form of what's called a page fault. A page fault, with a very scary name, is a message from the CPU that somebody just tried to access some memory, and I have no clue what on earth they are talking about. It basically says, I don't have any mapping from this virtual page which someone's trying to access to any physical RAM. And as such, we either need to allocate a new page frame, which is a physical page frame in memory, and set up the mappings for it, or we're going to access an invalid address. And we look at the permissions to work out which is which. So let's take a look at how this typically works. So from user space, an application typically requests memory through their libc's malloc, mmap, or something like that. This is true even if you use something like Python, right? Like when you create some object, it has to instantiate your memory, and it goes through the C API or whatever. If you use like some weird Python, then it's probably something else. But you have to do some kind of memory allocation. Importantly, these functions you're calling are in user space libraries. They are not system calls yet. What this might internally use is something like sbreak or break or mmap or some kind of system call which is designed to increase the virtual memory space. And these functions only increase the virtual memory space. Importantly, they don't do anything at all with physical RAM whatsoever. It's also possible that we just use some previously freed pages instead of allocating new ones. How exactly malloc goes about this procedure depends on your allocator and your operating system. But for now, the point is like, you've asked for some memory, we're going to give you some memory, and the lie keeps on going. So sometime later, the process then comes to actually go and use the memory. And what it does is it dereferences the virtual memory address in the process. Since the CPU has absolutely no idea what on earth you were talking about, it produces a page fault. And Linux now realizes that this memory simply hasn't been put in main memory yet. So what it's going to do is allocate a new page frame, which is a physical page in memory, and set up the appropriate mappings for it. If it then needs some data from a backing device, for example, if you now need to swap in some pages to satisfy that, it's going to copy those to memory before resuming execution of the program. Importantly, this is what I was talking about earlier, which is like we need to not involve the program in this process. From the processor's perspective, it has no idea that any of this happened. It just gets a page eventually, and that's that. The important bit to remember here is how disconnected a function like malloc is from actually allocating memory. Programs don't allocate real memory when they call malloc, they just get the option to do so. And there are so many indirections here that one has to be very, very careful trying to reason about what the application memory semantics and lifecycle should be. This is true in any language. I use C in my examples because it happens to be what I'm familiar with, and it's quite illustrative of this problem. But this applies to, use Rust, Python, Bash, whatever. They all internally use malloc infrastructure and have the same kind of situation. Okay, so Chris, you've told me that when I call malloc, it lies and it says I have some memory that it actually didn't give me yet. But at least when I call free, it's gonna get rid of the memory, right? They wouldn't lie to me twice, the bastards, would they? Of course they would. It's Linux kernel developer. Of course they would. So if this simple program allocates 1 megabyte, touches each page, it frees it, and then waits. If this looks like a lot of code, you don't have to look at it. You can just listen to me. So if you run this and check the RSS, the resident set size of memory after free, you would expect it to drop to 0, right? Well, it probably didn't. In fact, more likely, one of 3 things could happen, all of them confusing, and some of them even more confusing than others. First possibility is that absolutely nothing happens. It stays at 1 megabyte. What happened is the allocator just put your memory on a free list somewhere, and nothing was returned to the OS, nothing was reclaimed whatsoever, right? This is what happens typically with allocators like Google's tcmalloc, which very aggressively avoids syscalls, because otherwise, like doing a lot of these things involves syscalls, which are quite expensive. But it does mean we have this very weird disconnect where your program says, hey, no, I've freed memory. The kernel thinks, no, you didn't. And the allocator says, well, I don't know. So nobody's really lying with bad intent, but the abstractions are hiding the reality of what's going on here. The second possibility is that the RSS drops partially. So it's not 1 megabyte anymore, but it's some other value. The allocator was feeling generous, and it returned some of the pages to the OS. But it kept some because, hey, maybe I'll need that later, or maybe you're going to use that later, so maybe I can just return that instead of trying to get it from the operating system. That's more common with something like glibc or gmalloc. And the third possibility, and my favorite possibility, is that when you free memory, the RSS actually increases. An incredible outcome. I know it turns out that inventing computers was a grave error. This can happen because the free operation itself has to do things, right? It might allocate internal metadata, or the allocator might reorganize its memory pool and end up touching more pages or page tables. So in this simple example, it's somewhat less likely, but in a production workload, that can really happen in some perverse circumstances. One example is when you have to combat things like memory fragmentation or align towards other goals of the allocator. So you can end up with these perverse situations where you kind of temporarily increase memory after doing a free. Importantly, free is a signal to your memory allocator. It is not a signal to the operating system. It says, I don't need this anymore, not please give this back immediately. The allocator is deciding what to do. It's very much like saying, I'm going to leave this party now, and then waving goodbye to everybody. Maybe you did leave, or maybe you're found 3 hours later in the back doing sambuca shots. All of these are possible at the end of the day, and it was your declaration made absolutely no difference to the outcome. And this is why monitoring memory leaks in production is so tricky and cumbersome, right? Because a process that properly frees everything still might not actually free the memory. And modern allocators make a lot of different trade-offs for this. This is one example of why measuring RSS is pretty tricky on modern systems, and we'll come back to that a little bit later. Who do I see in the audience that I don't like? I see a conference organizer. Dan, why don't you step up to the plate? Dan, can you do me a favor?
Yes.
Can you read this slide for me, please?
Yes. Okay.
We're going to get very close, and you're going to use this microphone, young fellow. We're all friends here, Dan.
Good. Okay. Yes. Random access memory is a form of electronic computer memory that can be read and changed in any order, typically to store working data and machine code.
Wow.
A random access memory device allows data items to be read or written in almost the same amount of time, irrespective of the physical location of data inside the memory.
I can't believe you would lie to the ladies and gentlemen. I can't believe you would say such falsehoods in a place of this. You should really be ashamed of yourself, Dan. So let's look at two kinds of traversal. Thanks, Dan, by the way. So let's look at two kinds of traversal for some large two-dimensional array. The first loop uses column-wise traversal, while the second uses this row-wise traversal. So you might think, I have to access everything in this two-dimensional array, right, by the end. So why on earth is the second version 50 times faster? Because despite what our esteemed colleague and Wikipedia say, random access memory is actually very bad at randomly accessing memory. One of the reasons for this is because DRAM is organized into rows, and its operation is governed by what's called the ras-cas pre-cycle. I know, they didn't have a marketing team. RAS is row address strobe. Essentially, let's tell the RAM which row we should go and get and activate that row. Cas is column address strobe. Essentially now, okay, you have a row, now select which column in the row to select. And at that point, you get the data from the DRAM cells and you put it on like a data bus. Pre is pre-charging a row, which is basically setting like the bank bit line to a known voltage or something like that. DRAM cells are basically simple capacitors, so this is all required to, this doesn't really matter, but is basically to avoid interference with when you access a different row. You can really just think of pre-charge, you don't have to think about electronical engineering. Think of pre-charge as like, I'm done with this row. Like I can now move on to another row. The key insight here is you can perform multiple column operations on a single active row before you need to do another pre-charge. So in this column-wise traversal, in the first case, I need to first pre-charge the previous row of RAM. I need to activate a new row of RAM, which is RAS, and I need to select a column every single time. In the row-wise traversal, which is the second one, we stay on the same row for many consecutive accesses. And one RAS, then you do a whole bunch of CAS operations, and then minimal pre's. I can see a man is writing down what I'm saying. That must mean it makes at least some kind of sense. That's good. Or it means it makes no sense, and he's like, please fucking hell, like, get this over with. The difference here is enormous. So RAS and pre operations are extremely expensive. Compared to CAS operations. So row-wise access can be a huge amount faster from just the DRAM access pattern alone. I think a lot of us as programmers have this idea of like streaming data is somehow fast or like contiguous data is fast, but don't have any real reason to understand it. And this is one of the big reasons why. Reading sequentially is also a very much better use of caches. So a cache line is the smallest unit of data transfer between memory usage and a CPU's cache. Typically on x86 and x86-64, it's 64 bytes. And we read that as one contiguous aligned block. So if we read randomly, as in the first example, we're going to have to read a whole cache line and then throw it away every single time, right? But if we read in this sequential and contiguous manner, then we don't have to do that, and we can continue using the same cache line. Another reason that reading sequentially is much faster is that virtual memory is divided into these fixed-size pages, 4 kilobyte pages on x86 usually. And the translation lookaside buffer, or TLB, is a cache of virtual to physical addresses, and it's usually pretty limited in size. So when you do some virtual memory operation, this is the thing that eventually caches, like what physical page should I be talking to? If we dart around the address space looking for pages, as we do in the first example, we are going to have to keep thrashing pages in and out of this cache. But if we do it sequentially, we don't have to do that. We always have the cache entry that we actually care about available. Most modern compilers will also automatically do what's called vectorization of the second version using SIMD instructions. SIMD means single instruction, multiple data, and it lets the CPU process a bunch of different array elements with a single instruction. For those of you who know about SIMD, I think you may grossly overestimate how much it improves the performance here. The vast majority of the improvement here is none of these except for RAS, CAS, and PRE, the things that we don't talk about. We spend a lot of time as programmers talking about caches, SIMD, all kinds of stuff like that. But the most fundamental one is the way in which data is architected on the DRAM. You might notice I didn't mention prefetch. Prefetch is where the CPU automatically detects this kind of sequential access and loads a bunch of stuff in advance. In this particular example, it doesn't really help. It can help in some cases. But in general, the purpose of this slide is to think, when you're writing code, try to remember that despite the name, neither random access memory nor the CPU are very good at actually doing random access. One thing that's critical to understanding Linux memory management as well is that Linux has these different types of memory. From the CPU's perspective, there's really no difference outside of some very basic things, but Linux treats different page types as being semantically different. For example, anonymous memory is, as the name would imply, not backed by any backing store. So that's the memory which you tend to allocate by malloc or that kind of stuff during the program lifecycle. Most people also know about caches and buffers, kind of two sides of the same coin. Nowadays, they're all unified. We have a thing called a unified page cache. But if you ask most Linux admins, they will say, oh, page caches, buffers, they're reclaimable, right? I can just free them anytime. If somebody wants the memory, I can just free them. The problem is that's not what reclaimable means. Reclaimable means if you ask really nicely and the pages are aligned with the order of planets, then maybe some reclaiming will be allowed to happen at 3 o'clock on Tuesday. It does not mean, oh my God, something bad has happened and I've got to allow you to do it right now. No, it doesn't care. It doesn't care about your needs. Your emergency is not its priority and it will get back to you. So for example, if some application is hammering on some file, it's very, very unlikely we're going to just drop that file from cache, right? So while it can be freed trivially in some circumstances, it doesn't have to be the case, which can cause some confusion when people inevitably come and say, why is my application ooming when I have tons of buffers and caches? Well, probably they were essential. The fact that caches can be essential is also an example of why RSS, the resident set size, a metric that people love to measure and is absolutely everywhere in every tool possible, is bullshit. And the reason for that is that RSS skews a huge amount of attention towards a very few select types of memory, in this case anonymous memory and mapped file memory. And we forget, though, that a lot of workloads simply cannot operate without a huge array of buffers and caches. We measure RSS because it's really easy to measure, not because it's a good measurement. And so when somebody asks you how much memory does your application actually use, unless you've done some tests where you've compressed it until the point where performance drops, it's very hard to actually give an answer to that. In one case inside Facebook, a team that had for years believed their memory footprint was like 100 to 150 megabytes on every single machine across the fleet, found out with the metrics we're going to go over in this talk that it actually was about 2 gigabytes on each machine, which is a humongous thing to not know. This is one reason why in modern resource control, we typically limit all types of memory together instead of trying to just, for example, limit anonymous memory. Because if you do that and ignore the page cache, for example, you're still going to trivially allow applications to break out. Another key building block of modern memory management is this thing called Cgroups. So Cgroups are a kernel mechanism we've built to balance and control things like memory, CPU, I/O, things which you share across a machine. They're essentially a user-defined group of processes which get some kind of set of resource limits. Usually you have like one Cgroup for something that's involved in effectuating a service, so like a daemon or something like that. I'm sure if you've operated containers before, you may have come across them. Every single modern container runtime, Docker, CoreOS, Kubernetes, systemd, nspawn, this kind of stuff, it uses Cgroups under the hood. And the reason for that is because Cgroups solve a huge amount of the long-standing problems and limitations we've had with traditional Unix memory management, like ULimits and the like. Cgroups have existed for 14 years now. They've changed a lot in that time. Most notably, a bit scarily, almost 10 years ago in 4.5, kernel 4.5, we released Cgroup 2, and now I feel very old. I gave a whole talk at around that time on why we were moving to this interface and not just making kind of incremental improvements to the old one. I don't have time in this talk to go over it, but if you're interested in a very in-depth discussion of like what the limitations are there, this talk is a good resource, and there's a link on the bottom. But the most important thing to know about Cgroups that's important for this talk is in Cgroup 2, we limit all of the memory together, right? So we have this memory.max file, which limits not just based on RSS, but really everything. That's like caches, buffers, sockets, kernel memory allocated for your application, all kinds of stuff together. And this is a step change from the old days of per process limits or Cgroup 1 limits, where you only limit like a subset of memory types. So on the surface, this looks like it should work pretty well, and it does. It does exactly what it says on the tin. It sets a maximum amount of memory allowed to be consumed for the Cgroup. But the problem is, how on earth do you use this to compose a reliable system? So let's say you have a couple of slices. The names in here are systemd terminology. Cgroups doesn't care what the names are, but in systemd terminology, a slice is basically a sub-part of the hierarchy for some class of application. So in best effort.slice, you'd put best effort services, and in workload.slice, you'd put like whatever you actually want to run on the machine. So a best effort application would be something like configuration management or metric collection, things that are really nice to have and I really want them, but if they don't run because the machine is completely oversaturated, then that's fine, like I can deal with that. The workload, on the other hand, is containing the applications that you really need to run on this machine. For example, HHVM or Nginx on a web server, or MySQL on a database server. The thing by which, if you do not run this, the whole point of this machine is completely moot. So the typical system administrator, or SRE, trying to be very responsible, might have a way of thinking that goes like this. You are scared that some best effort application might have a memory leak, and what might happen is it might oom the entire machine. Oh, that would be really bad, wouldn't it? That would be quite bad. So I'd better set a memory limit on besteffort.slice, and I'd better put it in besteffort.slice. Oh, but now you've put it in besteffort.slice, and there's a whole bunch of really, some of that stuff is actually quite important. I better make sure he doesn't do anything to cause any problems with the others. So now I'm going to actually put a memory.max on that thing as well, and make sure it can't burst outside of its own limits. Oh, but now I'm particularly worried that my main application might actually, do a global oom on the machine. If it were to cause a oom, I would like to, only have a very controlled one that doesn't take down the machine. And so on, and so on, and so on, and so on, until you have an outcome by which nobody can tell you how the machine is supposed to work anymore. Inevitably, what's going to happen is one of these is going to grow a little bit in how much memory it uses, and then you're going to have to reason about, how on earth am I supposed to do resource distribution on this machine? This is even infinitely worse if you work somewhere like Facebook or Google, or in some company where you have thousands of services and you have a bunch of teams developing them, and there's a disconnect between, I want to deploy this feature, and oh my God, what should the memory limit be? Like, those two things never occurred in the programmer's mind. So our ultimate goal here is to just keep whatever is in workload.slice running right. What if we could just encode that? What if we could just write something like this? So memory.low is a fundamental change to the way that we've gone about controlling memory on Unix for the past 50 years. The idea is that instead of trying to control memory by putting every application into a very tight coffin, the idea is to instead have, say how much memory our primary workload needs to operate, and then let the system sort it out. But how does that actually work? So all of this works based on reclaim. Reclaim is a fancy term for this process of trying to free some pages. Reclaim either happens based on global memory shortages, or it can happen if you brush up against a limit within your Cgroup or stuff like that. So memory.low hooks into the kernel's reclaim infrastructure and does what's called protection. For example, if you have memory.low set to 20G, then as long as you're using below 20 gigabytes of memory, we are going to generally exempt you from having memory taken away from you. This means that we tend to reclaim instead from everybody else, and the only time we dip into your reserves is if there's an immediate and kind of global critical shortage. This might sound kind of simple, but in reality it's been pretty non-trivial to implement. For example, if multiple protections on the system are competing against each other, we have to decide how to handle that. We also have to decide how to handle distributing protections from a parent to a child, especially when children compete with each other. And we also need to handle the case where you're slightly over your memory protection. So in that case, we usually reduce the amount of scanning we do for pages from you proportional to how far over your protection you are. A really nice effect of using this instead of memory limits is that this is work conserving, or at least more work conserving. Because it's not a reservation, right? We don't take 20 gigabytes of memory away from everybody else. As long as you don't affect others, you can use as much memory as you like. You can go and use that part of what would be like that 20 gigabytes if it was a reservation. The only time we actually make it happen is if that application which is protected demands to use it. This is much more tolerant of temporary spikes and changes in memory composition, and we now primarily rely on this to do protection and memory protection within Meta. There are still some kind of cases where limits do make sense, but they are generally somewhat more limited. We've generally transitioned towards using memory.low and memory.min. This brings us somewhat neatly onto swap as well. A couple of years ago, I wrote this blog post called In Defense of Swap. I wrote this note because we just had a newsfeed outage, which I'd investigated. And in that newsfeed outage, I had looked at the machines, and my conclusion was basically, if you had been running with swap, it probably wouldn't have happened, which was not pleasing news. If you haven't read this blog post and perceive it as not useful, I strongly recommend reading it. I will give a brief go over of it here, but it is kind of a long topic. In general, a lot of people think swap is mostly irrelevant nowadays because we've got tons and tons of memory. This is kind of strange, though, because swap and memory are not two interchangeable ideas. For the things that swap is good at, you really can't get them any other way, and the things it's bad at, you usually can mitigate those. Usually, these discussions hinge on misunderstandings about what swap is actually for and good at. And swap has almost absolutely nothing at all to do with this concept of being emergency memory or like backup RAM or like slower RAM, as some people believe. You also will see people online saying stuff like, oh, I don't use swap because then memory can turn into disk I/O. But this obviously makes no sense, right? Memory turns into disk I/O whether you use swap or not. Because if we can't evict anonymous pages, which are what are allowed to be evicted with swap, what we're going to do is we're just going to thrash the file cache, right? We're going to just evict stuff from the file cache, and now you have to go get the file cache stuff from disk. It's even worse because we have a smaller pool of pages from which to pull from. So these kind of misunderstandings have really hobbled swap's reputation and led to these misconceptions that it's not useful if you have a lot of memory available. So if it isn't a mechanism to kind of expand your RAM, what is it? So swap allows reclaim on types of memory which would otherwise be M-locked. That is, it provides this backing store for memory which is otherwise essentially locked in RAM. It also allows to more gradually ramp up memory contention, which would otherwise ramp up in a binary way, right? Because if you don't have swap, it's you could go from making optimal use of the system to going, oops, one page over and now we're completely deadlocked. This is because running out of memory becomes extremely fast and extremely binary. Another thing is that if you've compiled things, you've probably seen this kind of like make j cores +1 stuff. Why do we do that? Why do we do cores +1? Wouldn't we want just the number of cores? Well, we do that so that we fill any slack remaining from increases or decreases in demand as they happen. And we want to do the same thing with memory, right? We want to always be pushing just a little bit of positive pressure so that we can make sure we're using everything that we have. And this comes back to what I mentioned earlier about us wanting to, as the operating system, promote the most efficient use of memory possible. And we want to do that without affecting the system latency too much, so it should only be a little bit of positive pressure. That is pretty much impossible to do if you don't have swap, because memory contention increases become extremely fast and extremely difficult to judge what to do about. That is when we go over the edge, we start spinning on recycled pages so quickly that we can't make real forward progress anymore. Swap does come with some trade-offs, which I go into in the post, but in general it is a very positive thing to have in your system. And if you're generally of the opinion that it's not useful, strongly recommend reading the post and yeah. So you thought, we already trapped Dan with reading the RAM Wikipedia page. I'm now going to trap you all. Who wants to tell me how you can view memory usage for a process in Linux? Wow, I've really scared the room down. Okay, somebody said top. I love you. Whoever is at the back, I love you. So top and the like tend to really only measure one type of memory. Okay, so they have different columns for different things, but fundamentally the big one that you get presented at the front is RSS or PSS or something like that, right? Importantly, they have no idea about any caches you might be using. And you might be thinking, hey, that's fine, those caches are just optional, right? The problem is that the answer is almost always no for any sufficiently complex application. So let's take Chrome just as a facile example. The Chrome's binary code segment is over 130 megabytes. He's a chunky lad. He's a big boy. We load this code into memory. We're not maniacs. We do it gradually. And we do it just like everything else as part of the page cache. But if we want to execute some part of that code, that piece of cache is not just something I can reclaim anytime I like. I need it in memory or the program's not happening. The same goes for caches for the files that you're explicitly loading during program execution, right? Eventually, those pages have to go to main memory for you to access it. So in Cgroup 2, we have this file called memory.current that measures the current memory usage for the cgroup, including everything like caches, buffers, and so on. So job done, right? Well, one of the more common things that happens when I come to some place like this and say, don't measure RSS, is people say, okay, I'm going to set instead I'm going to measure memory.current. Memory.current is a file that, as you might guess, shows all of the memory currently used by the cgroup. But it's quite important to know what that means and what the differences are. The very fact that we're not just talking about RSS anymore, but kind of every single kind of memory that's being used by that application, like caches, buffers, socket memory, whatever, all of that is in memory.current, and that's how it should be. Because if you didn't do that, then we wouldn't be able to prevent abuse of system-wide resources. But at the same time, it does present a very different paradigm to reason about. So understanding why it is more complicated to reason about memory.current than it seems comes down to why we as an industry gravitated towards RSS as a metric. The reason people chose RSS as a metric is because it's pretty stable. It's generally relatively static. It doesn't move around a lot, it's easy enough to set a limit on it, and it makes you feel good at night having that little metric that would page you if it went over something, even though it does absolutely nothing. For example, like memory.current suffers from exactly the opposite problem, which is it tells you the truth, and people have no idea how to handle the truth at all. For example, if you set an 8 GB memory limit and your application runs overnight, and there's no system-wide memory pressure, what's the value of memory.current going to be? It's going to also be 8 GB. Why is it going to be 8 GB? Because we just filled that with all kinds of nice stuff to have, right? We filled it with buffers, caches, all kinds of nice things. It's not that you need 8 GB. It's that we've given you 8 GB because nobody else asked for anything, so why not give it to you? So if there was no pressure for it to shrink, then how can we tell what the real needed amount of memory should be at any given time? Let's take an example kernel build. So this kernel build with no limits has a peak memory.current of over 800 megabytes, or just about 800 megabytes. In Cgroup 2, we have this tunable called memory.high, which reclaims memory from a cgroup until it goes back under some threshold. So right now, with no limits, it takes about 4 minutes to do the build, and it takes about 800 megabytes. When you apply a 600 megabyte limit, though, it actually takes pretty much exactly the same amount of time with 25% less available memory. The same even happens when we set it to 400 megabytes. Now we're using half the memory, and you have like 3 more seconds of wall time. Pretty good trade-off. But if I dial it down to 300 megabytes, then things never even complete. You know, you're 9 minutes in, and it's not done. You have to Control-C it. So we know this process needs somewhere between 300 to 400 megabytes of memory to operate with reasonable performance. But finding this exact cutoff is a very tedious trial and error process. And this trial and error process also only works for highly uniform jobs, like this example, but not for something like a web server. So to get an accurate number, we need a different way. So Senpai is this self-contained tool that uses Cgroup 2's pressure stall information, or PSI system, to find out how much memory your application actually needs. So PSI is one of the new technologies we've been developing for Cgroup 2 to determine whether a particular resource is oversubscribed. Now, we've never really had a metric like this in the kernel before. We do have very many related metrics, like memory usage, as shown by like free or top or something, page caches and buffer usage, page scan rate, stuff like that. But even with those metrics, it's very difficult to tell efficient use of the system from oversubscription. In Senpai, we use these metrics, which measures the amount of time that threads on the system were stuck doing memory work. So for example, this pressure equals 0.16 thing means, 0.16% of the time within some time window, I was doing some work which I don't think I would have had to do if I had more memory. This could be things like waiting for kernel memory locks. It could be things like being throttled. It could be things like waiting for reclaim to finish. Even more than that, it can be things like I'm waiting for some memory-related I/O, like I'm refaulting page content into the page cache. I'm swapping in, stuff like that. It's essentially saying, if I had more of this resource, yeah, I could have run 0.16% faster. So using PSI and memory.high, Senpai applies just enough memory pressure on a cgroup to evict cold memory pages which are not necessary for workload performance. It's basically an integral controller which dynamically adapts to these peaks and troughs. Like a web server, you have more requests coming in, then we expand. If you have fewer requests coming in, then we shrink. So what it does is provides a memory working set profile of an application over time. So it can be used to answer the question, how much memory does this thing actually need to run? In this case, we find the answer is like about 340 megabytes. And to get there, we just keep on pushing the application's memory limits down until we start to see problems or we start to see this pressure, and then we back off just enough. So why would anyone want to do this? Why don't we just let the applications kind of run free, right? So as I mentioned before, in terms of observability, we had a team which for years believed they used 100 to 150 megabytes, and this was the method by which they realized, actually, my application needs 2 gigabytes on every machine to run. And we use this to kind of find these regressions and leaks in a way that RSS measurement can't really do. Another thing we use it to do is to amortize memory shortages and kind of get ahead of things. So when a machine is already very heavily contended, it can be quite hard to free memory quickly because resources are already quite scarce, right? So we can avoid these situations in the first place by doing it when things are kind of going okay. The combination of these things means that Senpai is an essential part of how we do workload stacking at Meta, because it not only gives us an accurate read on what the workload's needs are right now, but it also allows us to monitor over time and adjust like the stacking limits as necessary. So this example we saw at the beginning probably seemed pretty simple, right? Allocate a megabyte, put a string in it, and print it out. My goal in this talk was to help you kind of learn how much more complicated even just like a facile example like this is behind the scenes. Even just this program exercises, page faults, caches and buffers for linked library slabs, all kinds of stuff that's really important. And if this example is hard to reason about, how much more complicated is your service going to be in production, right? How much harder is it going to be to reason about and debug? I really hope this talk has given you some of the tools and techniques needed to understand and reason about some of that complexity in your own services and applications when designing and debugging them. And I'll be around in the conference if you want to discuss anything from these slides or go over anything related to your services. But until then, I've been Chris Down, and thank you very much.